Assalamualaikum warahmatullahi wabarakatuh and good morning. So, can you guys hear me? Can anyone respond? Because I didn't hear anything. Okay, good. Right, nice. So, okay, so let's start. So today we're going to just continue our chapter for discrete Fourier transform, which is a very important topic because this topic and the last two topic will be, there are a lot of questions in the final exam later. Okay, so today we're going to look at another example. So we have seen two examples last Tuesday. So we have seen one example on doing a forward DFT, and then we have seen one example on inverse DFT. And today we're going to look at another example. So this is example 3. So what is the example? So compute DFT for signal xt, which is equals to cos 4000 pi t for t, which is starting from 0 up to 0.5 millisecond, right? And the frequency sampling for the signal is fs equals to 10 kilohertz. So in this example, we are given a signal, so which is in t. So this is not on n. Okay, so this is a continuous time signal. And but of course, this signal can be will be sampled using fs equals to 10 kilohertz. So now, in this example, we will see because k, which is the frequency for discrete Fourier transform. So the one is the k. The unit is there is a no unit. So how do we relate to this frequency, which is in hertz? Okay, so this is the example. What example is? All right, so because this is in a continuous time, so what should we do is actually the first thing, we need to convert the signal into discrete signal, discrete time signal. Okay, to be specific, this is a discrete time signal. So, and what is the relationship? So we already know that the relationship is T equals to NTS. Or, of course, this is actually N over Fs. Okay, because this is actually a frequency in hertz, and we want to have a DFT, which the frequency is in a discrete frequency. So let's see. So if we look at this slide, so actually we have this thing, but we want to have a spectrum which is in K. So we need to go through two sampling process actually. So the first one is the time sampling. So this is time sampling. So we have a Fs, and then the second one is we should do a frequency sampling. So which we need this capital N. Okay, so now we are doing the first sampling process, which is t equals to nts, or t is equals to n over fs. So this is our t. So whatever you have, you do. So this is where we can convert that into n over fs, or n over, no, here we have 10,000 hertz. Okay, so that's our fs. So what we have now is this is a xn, a discrete time signal, so which is equals to cos 4000 pi. So then replace that t as n over 10,000, and then this is the range. The range is from 0 up to 0.5 millisecond. 0 is of course a 0, and then t, now we replace it with n. Okay, and this one, so because this one is originally this is t equals to 0.5 millisecond. And what is actually n? N is, if we are looking at this, if we look at this equation, so n is actually equals to t multiplied by fs. T fs. And so this is where we have 0.5. A milli is actually equals to 0.0005, and then you multiply by 10,000. Right? Because that's your t, and then this is your fs. Okay, so this is where we have a 0. N is actually from 0 up to less than, this is less than. Be careful, this is less than 0.0005 times 10,000, you will get 5 over here. Okay, so then we will have n from 0 up to actually 4, not 5, because this is less than 5. So 0, 1, 2, 3, 4. So this is where we have it. 0, 1, 2, 3, and 4. Okay. So this is where, again, if you realize, if it is in a continuous time, so you can only represent the signal using some equation. And this is the equation for our continuous time signal. But if you have a discrete time signal, so you can also represent it either using an equation, this is this equation, or as a series of values, which we call a vector. Okay, so we cannot have this vector if we are having a discrete time, a continuous time signal. So it's not possible, because the vector will be infinity. You will have an infinity number of points for this one. So that's why we have this. So and then this is actually very short, because we have only 1, 2, 3, 4, 5 samples. Okay, because of course this is example to show some concept. So that's why the signal is very short. So we have only 5 samples for XM, and of course in real application, so you will have at least maybe 1,000, 2,000, maybe 10,000 samples. Okay, and maybe more than that, because if you have fs equals to 10 kilohertz, so you will have a 10,000 sample in just 1 second. If you are recording for, let's say, 1 minute, so you can just multiply that. Okay. All right. So then we have seen this in our Tuesday class to compute the DFT. So this is actually the formula. So it's just a summation of n from 0 up to 4, because we have our signal in time domain of 5 samples, which is a 0 up to 4. And then this is the xn, and then multiply by e to the power of minus j2 pi k n over 5. Okay, so this is the n. So why we pick n equals to 5? Because this is actually the minimum value of n that we can have, that we can choose. Okay, because the length of the time domain signal is 5. So n is minimum as 5. Of course, you can pick n greater than 5. So the higher the value of n, the better the representation actually. Okay. So, but because this is just an example, so we're going to look at that one. And before we do this DFT, so let's see. Let's try to understand what is actually this signal is, because this is a very simple sinusoidal signal, but this is a cos. A sinusoidal signal can be cos or cosine. Okay, and why we are really interested in this thing, because of the a theory from Fourier, because Fourier says that any signal can be decomposed into a series of sinusoidal signal. And that sinusoidal signal is actually, each sinusoidal signal will have a unique frequency. It will have a single frequency. So this is actually the basic idea on how, on why we can actually transform this time domain into a frequency domain. Because every single sinusoidal signal is actually representing one frequency. Okay, and then this signal is actually one frequency. And what is the frequency? The frequency is 4,000 hertz. Okay, so if you look at, sorry, this is not 4,000 hertz. Be careful on that. So actually, this is we can have what we call a capital omega angular frequency, which is equals to 4,000 pi. Okay, and this is actually equals to 2 pi f. So that f is actually our frequency in hertz. So then what is actually f? F is actually equals to 2,000 hertz. Okay, so this is actually our signal. Our signal is actually a single frequency signal, And what is the frequency? The frequency is 2,000 hertz. So this is where actually what we are going to expect if we do a Fourier transform, which is, let's say this is f. So we should see something at 2000 Hertz. There must be some peak. Okay, previously if you do a Fourier transform, which is a transform for continuous time signal. Whenever you have a signal, something like this, let's say this is a cos, let's say this is A. So in frequency domain, this is XF. What should you get is actually A over 2. Right? So this is the amplitude. So actually you will get A over 2. So if you still remember, if you do a Fourier transform to a continuous time signal. And the rest will be, if this is ideal means, so it will be continue until infinity and from minus infinity. Okay, so this is actually what we call A cos omega t. Actually, the signal start from minus infinity up to infinity. Periodic. This is what we call a periodic. So then we have the amplitude. So we will have, if you do a Fourier transform here, so we will get one peak only. The rest will be zero. The rest will be zero. And that y-axis value, the magnitude, is actually A over 2. Okay? And if we look at this, our signal here, this is actually not starting from minus infinity up to infinity. It doesn't start with minus infinity and it doesn't end at infinity. So there is some limitation here. So the period is just a very short. It is from 0 up to 0.5 millisecond. And actually what will happen here is you're not going to get this kind of thing, a perfect single peak over here. So what you will get is actually something like right? So you're going to have what we call a side lobe. So this is actually what will happen because in this signal, so of course we can see this is a cos 4000 pi t, but if the period is just from 0 up to 0.5, this is actually no more a periodic signal. Okay, this is actually aperiodic. So because it starts at 0 and it stops at somewhere, right? It is no more periodic. So, but still, we will see a peak, a highest peak at that frequency, at 2000 Hertz. The rest, maybe you will see some values, but not as high as the value at 2000 Hertz. Okay, and when we do DFT for discrete, discrete time signal, we will see almost the same thing. We should, okay, we should see almost the same thing because actually it doesn't change anything. What's changed is just the value. The value becomes discrete. Okay, so let's do this. So this is actually what is the expectation. So we should see some peak. And the rest, if we have values, it should be lower than this peak. Okay, the magnitude should be lower. All right, so now to make this example simple, so that's why we just choose n equals to 5, which is the lowest value that we can have for n, because that's the rules. That's the rules to pick n value. Okay, so you can choose this as the 1000, 2000, 10,000, 100, 10, 20, no problem, as long as it is higher than or equals to 5. Okay, so now let's do that. So plug in the value. So now because we are having n equals to 5, means that, so what does this mean? So we're going to find xk, where k is also from 0 up to 4. Okay, so we need to find x0, x1, x2, x3, x4. So where you have five points or 5 samples. So the first one is always the easiest, where we find x0. So this is where k equals to 0. When k equals to 0, replace this k. So you just replace this k with 0. If this k is a 0, everything else becomes 0. And then this is actually equals to e to the power of 0 equals to 1. Okay, so then what you will have is only a summation of n equals to 0 up to 4 of all the xn. Okay, and the rest, you just multiply by 1. So this is where we have, the first one is 1 if we look back at our signal. So this is xn. So we have the first one 1, and then 0.31 minus 0.81 minus 0.81, and then 0.31. So yes, this is the easiest. So what we will have is just a 1 plus 0.31 minus 0.81 minus 0.81 plus 0.31 equals to 0. Right? Okay, finish. X0. So next, let's move to x1. So this is where k equals to 1, because we need to find xk from 0 up to 4. Why? Because the n is equals to 5. If this n is equals to 10, you need to find x0 up to x9. Okay, so that's depend on the n. And again, why we choose 5? Because of 5 is the minimum value that we can choose for this example. Right? Okay, so then we plug in the value again. This is k equals to 1 now. So we have this k. Now k is equals to 1, so everything becomes a minus j2 pi n over 5. Expand this thing. So this is what you will get. 1 plus 0.31 e minus j2 pi over 5, and the rest. Okay, and actually this is quite interesting, because if we look carefully, this one and this one, so actually we can group it as this, because this is minus j2 pi over 5. Okay, no problem. And this is actually minus j8 pi over 5. So this is actually equals to positive j2 pi over 5. Okay, so why we do this? Why we need to identify this and convert this into this one? Because if we group this into as a single as one set, so later we can have as a 2 cos 2 pi over 5. So it will make our calculation easier. Okay, but first thing, of course, you need to identify that, okay, this is minus j2 pi over 5. We know that this is minus j8 pi over 5 is actually equals to positive j2 pi over 5. So how is that? So because we have everything is in angular. Why it is in angular? Because this is a complex value. Okay, so this is a complex value. So all values is actually in complex value. So that's we have. So we have a real and imaginary value. And the first one, this is actually a 2 pi over 5. So what is it actually minus 2 pi over 5? So 2 pi over 5 means because this is 0, this is actually pi over 2, this is pi, or if we go back the other direction, this is minus pi over 2, this is minus pi. And minus 2 pi over 5, so we need to divide this half of this plot into 5. So let's say something like 1, 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, not including this one. So just this one. So 1, 2, 3, 4, 5. Okay, and what is 2 pi over 5? So this is 1, 2. So this is actually minus 2 pi over 5. Okay, so this one. And this is actually minus j8 pi over 5. So if you count, this is 1, 2, 3, 4, 5. We did 8. So maybe we have another one. So 1, 2, 3, 4, 5, 6, 7, 8. So this one is actually minus 8 pi over 5. Okay, then of course we can have on a different direction. So this is actually equals to 2 pi over 5. Okay, what? 2. So that was a 2 pi over 5. So actually we are having this one and this one. So one at a positive direction, another one is at negative direction. So this is where we can, by knowing that, so we can group it so that we can have a 2 cos 2 pi over 5. And this is the same thing here, So this is a 4 pi over 5, minus 4 pi over 5. And this is a minus 6 pi over 5. So actually this is a minus 6 pi over 5 is equals to 4 pi over 5. So you can group that into 2 cos pi, 4 pi over 5. Okay, then solving that will be much easier. Okay, of course, you can solve this one by one. No problem. Do this, cos minus j sine. This one also, cos minus j sine. This is another one, cos minus j sine. And this is another one, cos minus j sine something. Okay, so if you do that, so means that you need to have, this is 1, 2, 3, 4, 8 terms. Plus this one, 9 terms. So, but if you do this, so it will be much easier to solve it. Okay, then after that, do the calculation, you will get x1 equals to 2.5. So this is actually 2.5 plus 0j. Okay, because actually everything's supposed to be in complex value. So it just happened that the imaginary value here is 0, right? And make things easier. Okay, then so this is x2. Same thing, plug in the value. So now it becomes hn e to the power of minus j pi n over 5. And then you will get, after you expand it, you will get something like this, because we have seen that pattern. You can group that previously in x1. So actually it will be the same for x2. So now you can group this one and this one. So it becomes a minus j 4 pi over 5 plus e j 4 pi over 5. Same thing here. And then you will get 2 cos 4 pi over 5 here. And this is a 2 cos 2 pi over 5 here. Okay, and then just solve it. You will get, at this case, 0. Right? So do everything. Lastly, you get 0. So then it's good. So, and same thing here. So what does this mean? So this is actually plus j0. The imaginary is also 0. Right? A very simple example, because what you will get is only a real value, no imaginary value. So based on symmetricity properties of the Fourier transform, okay, actually you doesn't need to calculate x3 and x4. So because we already know that, so you can skip computing x3 and x4. Again, if we are looking at omega, so first we are looking at omega first. This is a 0. This one's supposed to be 2 pi. This is pi. So this is actually the symmetricity line. Okay, so we can call that symmetry line. So if this is A, this is B. So we already know that. So whatever in A, B is actually just a conjugate of A. Okay. So this side is just a conjugate of this one. And of course, this is the same. So A is actually just a conjugate of B. And now we have a k, so which is the n is equals to 5. So then we know that. So what is the delta omega? The delta omega is actually 2 pi over 5. Okay, so that's the delta omega. So we will start at 2 pi over 5, and then 4 pi over 5, and then 6 pi over 5, and then 8 pi over 5. So what you will have is something like somewhere here, 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 and over there. Right, so this is your 0, 1, 2, 3, 4. This is 2 pi over 5. This is 4 pi over 5. This is 6 pi over 5, 8 pi over 5. So, but the key is 0, 1, 2, 3, 4. So we can see that here. So actually 0, 1, and 2 is in the A region. And 3 and 4 is in the B region. So this is where we doesn't have to compute B, because we already know that B is actually equals to conjugate of A. So this is where we can conclude that x3 is actually a conjugate of x2. Okay, this one's supposed to be conjugate, and this one's supposed to be a conjugate pair. So then x3 is a 0. So then 0 is a 0. Okay, because the conjugate is you change sign on imaginary, so it doesn't have imaginary value here. And x4 is actually a conjugate of x1, so which is equals to 2.5. So then, so this is what we have. Xk is equals to 0, 2.5, 0, 0, 2.5. Okay. So this is x0, x1, x2, x3, x4. And this is in xk. So if we want to plot that, so we can plot this xk. So 0, 1, 2, 3, 4. So this is at 2.5. This is at 2.5. This is 0, 0, and then this is 0. So we have nothing on 5, because 5 is actually equals to 2 pi. So we don't take that, right? So 2 pi is here. Actually, this is 2 pi somewhere here. So this is pi for the omega. And because we have fs, so we have fs. So if you have fs, so what you can do is, instead of xk, actually we can plot xf, right? So this is a capital F. So because we have both, so we have a capital N, which is equals to 5. So we have fs, which is equals to 10,000 hertz. Okay, so let's convert that. So the frequency value in hertz for each DFT point can be found using F equals to kfs over n. Okay, so this is the formula. So if you look at here, so actually this is the formula. F is actually equals to fsk over n. And you doesn't have to memorize this formula, because this formula is given in exam. Okay, so let's do that. So k 0, then f is a 0. If this is a 0, then everything comes 0. And k equals to 1 and 4. 1 and 4. 1 to 4. So this one, if this is a 1. For k equals to 1, then f is actually equals to fs over n. And fs is 10,000. So divide by 5, so you will get 2,000. Okay, so that one is a k equals to 1. So k equals to 4,000. K equals to 3, supposed to be 6,000. So is that correct? So let's check. Okay, because if we are plotting on a capital F in hertz, so we need to know something else. Okay, so we need to know this thing. So there's a rules for that one. Okay, let's check again this one. So we have actually 3 types of plots. This is what we call a whole plot. So where you will have your range from 0 up to, actually this is n is actually at 2 pi, but of course we will have up to n minus 1. Omega, it is starting from 0 up to 2 pi. But it's a small f and it's a normalized frequency, so actually the range is from 0 up to 1. But if we look at this carefully, so if you have a frequency in hertz, so actually this is from 0 up to fs over 2. And then we shouldn't plot on the second region. Okay, this is on the conjugate. On whole plot, so actually you cannot plot that because it will not be accurate. So this is if in our example, so this one will be 2000, this one will be 4000, and this one will be 6000. So that 6000 is an error. Okay, so because we doesn't have that. What is the maximum frequency? Maximum frequency is fs over 2. At this point, this is actually fs over 2, which is equals to 5000. So it's not possible to have 6000 hertz. It's not possible to have 8000 hertz. Okay, because the maximum frequency, so what is this? So this is actually maximum frequency. Because we do sampling. Sampling says that your maximum frequency is actually fs over 2 because of that NIQs. Okay, so this is why actually if you want to plot it on a frequency in hertz, you cannot do whole plots. So it will be wrong. Okay, so what you can do is just either use half plot, because half plot is just a 0 up to fs over 2. So that will be true. Okay, you won't involve the 6000 and 1000 hertz in our case, in our example just now. Or you do shifted plot, because a shifted plot, this region will be shifted to the negative area. And this is actually no problem. So this is actually good. So what you will have is actually from minus fs over 2 up to fs over 2. So this is still correct. This one, so that's why I put it here, NIL. Right? So you shouldn't have that. So in that case, so this is why in our plot here, so I'm using a shifted plot. So this is actually whole plot. No problem for K, because this is K. But here we are using frequency in hertz. So we cannot use whole plot. So actually this is shifted plot. Okay, so you can either use shifted plot or half plot. Okay, so then this is where we have a 0, and then at 2000 hertz, so you will have that 2.5 magnitude. And 4000, which is a 0, minus 2000, this is just a negative frequency of this one, the mirror. So same thing, 2.5, and then minus 4000. And if we look back at our example, our original signal, the time domain, so it is true, because what is our f? The frequency in hertz for this signal is 2000 hertz. Okay, so that's why we have this is actually expected. So this is to confirm that. So our plotting is correct. So you have one peak at 2000 hertz, because that is actually the signal is. The signal is having one frequency, which is 2000 hertz. So this is where we see that the rest is just 0. The rest is just 0. Okay, and this is in K, that 1, K equals 1 is actually representing frequency at 2000 hertz. Okay, so any questions? This is very important, because now we can analyze that, because what is the purpose of doing spectrum on input signal? Because we want to identify unwanted signal, unwanted frequency, right? But of course, this is we doesn't have any objective on removing any frequency. But we can see that if we have a 2000 hertz signal, so we can see it on frequency domain. So this is our DFT plot. So we can see that on DFT plot. Either you use K, either you use frequency in hertz, either you use in omega, you're just converting the frequency. Because we have 5 types of frequency. Okay. Okay, so if there is no question, so let's move to our next example. So actually, when I skip an example, so means that I'm not going to emphasize this points this semester. All right. So this one skip, because we doesn't have much time this semester. A lot of a break actually. So relationship of DFT to DTFS, skip. So skip. So a lot of things should be skip. Skip. So skip this one. And of course, this one is important because symmetry properties of DFT is actually, this is the same with symmetry properties of DTFT. And actually we have seen this. So which is Hk is just equals to Hn minus k, the conjugate. Okay, so that's actually the symmetry properties. Where is the symmetricity line? At omega equals to pi. Okay. And then okay, so let me check. This example is actually related to there's a formula list that we have seen previously. A DTFT symmetry properties. Okay, so if your time domain signal or system is real and even, so actually we have a different formula, okay, a simplified formula. Okay, if it is real and odd, so we have a simplified formula also, because these two is actually symmetry. This is a time domain symmetry, right? So instead of using the original formula, so in the next example, so we're going to use this formula, but of course not on omega, on k. So because omega and k is just, what is omega? Omega is just a 2 pi k over capital N. Okay, just change that. Okay, let's start. So hopefully we have time to finish this example. Because why this is important? Because if we know our impulse response or our signal is actually symmetry, so we can solve it faster and easier because we can use a simplified formula. So instead of using the original formulas, such as we have done that in our first 3 examples. So we are using the original formula. But now we're going to use the simplified formula. Right? Okay, so let's say we have a system. Okay, this is what we call an impulse response. And what is our impulse response? So we have a 1, 2, 2, 2, 1. And this is actually symmetry. Okay, so or to be more accurate, this is a delayed symmetry. So how much is the delay? So if we if we observe this, so actually it will be symmetry at that point. So if this is at 0 originally, if this is symmetry, this one's supposed to be at n equals to 0. But now, because the n equals to 0 is here, so actually this is already delayed by 2 samples. Okay, so in this case, by 2 samples. Right, then we can use a simplified formula. So which is we can use this one, and we can see that that one is actually an even signal. So that one is an even signal. That one is not odd signal, right? So then we can use this formula instead of this formula. We use this one. Okay. All right. So for even signal Hk, which is it will be equals to e minus 2 pi k over 5. This one is actually already plugged in all the value here. Okay, so because what is actually the formula? So if we have Hn, 1, 2, 2, 2, 1. So actually we can have a H even signal equals to 1, 2, 2, 2, 1, which is centered at that one. Okay. And what is our frequency response of H K? So this is actually just let's do the omega first so that we can see the original formula. H omega is just E j omega of H E omega. Right? So missing one and ND. So this is actually the properties. So if you have a symmetry and then this is a delayed symmetry, so your frequency response of this is actually just you can do just multiply by e to the power of 1 minus j omega nd to hit this H E omega, right? Because this is where you can have your H E omega. And to solve this, you can use that simplified formula. Okay, just you need to multiply this one. And of course, if you convert that into HK, so this is because what is the omega? So it's lagging. Is it okay now? So maybe my internet has some problem. Okay, all right. So hopefully my line is okay. So that's later, if you are lagging, you can watch back the recording. So if this is a HK instead of omega, so what is the omega? Omega is a 2 pi k over n. So you just replace everything. So this is EJ 2 pi k over n multiplied by nd. Right? So we have that one. So you just replace that omega into this one. So actually this is what happened here. So this is actually originally from EJ omega nd. And this minus 2 is the nd. And this 2 pi k over n is the omega. Okay, so you just replace that. And the rest becomes, this is a HE0. Where do we get that one? From this formula. X0 plus 2 summation of xn cos omega n. Right? Doesn't have to memorize that because it's already in the formula list given in the exam. So this is the value. So this is a 2 summation of n up to 2 because we just do half of it. Just do half of it. If this is 0, this is 1, this is 2. Okay, so this is 1 and 2. So HEN cos 2 pi k n over 5. And then k values that are at omega less than pi is k equals to 0, 1, and 2. Why is this? Because we just need to compute half of it. Because the other half is just a conjugate. So it doesn't need to compute. You just take the conjugate of the values only. Okay, so we're going to compute only for 0, 1, and 2. H0, plug in all the values. This one becomes 0. So e to the power of 0 is 0, is 1. Okay, so this is 1. And then multiply. So this is HE0. HE0 is 2. This one. Okay, not 1 because this is HN. So what we need is HE. HE is this one is at n equals to 0. Plus this one, summation, everything becomes 0. So this is a cos 0. So cos 0 is 1. And then you multiply this equals to, this is 2, this is 1. Sorry, this is 2. HEN. So whatever it is, this is actually the value. Okay, I don't want to get confused with this formula. So actually, this is a 2, and then this is 2 plus 1. Because we have two things here. One is HE1, Another one is a HE2. Okay, so HE1, this is 2, and then HE2, this is 1. So 2 plus 1 multiplied by 2, and then plus 2, you will get 8 for H0. And then again, plug in all the values now for K equals to 1. So we have everything here. So plug in into 1. So you will get this one, 2 plus 4 cos 2 pi over 5 plus 2 cos 4 pi over 5. And then this is easy to solve. So you will get this value, 1.618. And this one is actually just cos 4 pi over 5 minus j sine 4 over 5. Okay, this one, this part. So you'll get this one. Then solve that, you will get minus 1.309 minus j 0.951. Okay, so now in this example, you see that we have a real and imaginary value. Previously, we just see some real value only. So now we have a real and imaginary value. And do that for H2. So after solving that, you will get minus 0.191 minus j 0.588. So another a mix of a real and imaginary value. And of course, we doesn't have to compute H3 and H4 because H3 is just a conjugate of H2. H4 is just a conjugate of H1. So then H4, because it is a conjugate of H1, you just change this sign. So H4 is a minus 1.309 plus J 0.951. H3 is equals to H2 or conjugate of H2. So this it becomes a negative 0.191 plus J 0.588. So which is this one? Okay, so that's H3 and H4. It doesn't need to compute that, right? Don't waste your time computing H3 and H4 because it's just a conjugate of it. And then because this is a complex value, so everything is in complex value, so then the magnitude is, we already know this, so it is a real squared plus imaginary squared, right? So just do that, so we'll get 1 by 1, so do that 1 by 1, so we get 8, this is 1.618, and this is actually the same thing. Actually, this is the symmetry line. Okay, so sorry for the interruption. So this is the symmetry line. So this is where we know that even if you do a magnitude, so you just compute the first three because the other two will be just the same because this is just a conjugate. This two is a conjugate. So for magnitude, the conjugate is actually the same value. Okay. And this is the phase. And we have seen this a formula in our previous example. So actually, if you want to compute phase, so you need to check the quadrant. So if the value is in quadrant 1 and 4, so you just do the normal tangent inverse. But if the value is at quadrant 2, the tangent inverse you need to plus with pi. And if it is in quadrant 3, so you need to minus with a pi. Okay, so if we look at our example here, so we will have H1. This is actually in quadrant 3, right? And this is also quadrant 3. So then, so this is where, if it is a quadrant 3, you need to, whatever you do on tangent inverse, minus with pi. Okay, so H0 is a 0, H1, and then minus by pi. So you'll get minus 0.8 pi. H2 is also in a quadrant 3. So, sorry, this is, maybe this is a minus. Minus pi, so you'll get a minus 0.6 pi. And then H3 and H4 is just a conjugate. For conjugate phase, the conjugate is, it will change the sign. So if this is a minus 0.6 pi, so it becomes 0.6 pi. Okay, magnitude doesn't change any, doesn't need to change the sign, but for phase, you change the sign. So this is minus 0.8 pi, so you will get 0.8 pi here. So then this is a full phase. The phase is for 5 point. So this is the first point at k equals to 0. And then minus at 0.8 pi, minus is 0.6 pi. So 0.6 pi, 0.8 pi, right? So then if you want to plot, this is a k. So let's say this is hk magnitude. So let's look at the values. 8, 1.618. 618. Oh, okay, everything is 618. So you will have 8 over there. 1.618. 1.618. 1.618. 1.618. So this is K0, 1, 2, 3, 4. And for the phase, this is K. For the phase is normally you will have your maximum at pi and your minimum will be at minus pi. Okay. 0, 1, 2, 3, 4. So the first one is 0 and then minus 0.8 minus 0.6. So 0, so minus 0.8 somewhere here, 0.6. So let's say this is minus 0.8 pi, minus 0.6 pi. And of course, this one will be somewhere here and then somewhere here. So which is, this is 0.6 pi, this is 0.8 pi. Okay, so then we can see that if it is a phase, so this one's supposed to be the center. If we are looking at omega, so this is actually pi. So this is anti-symmetry signal. So that phase is supposed to be such that it's always be anti-symmetry. And this one here is supposed to be the omega equals to pi. So it is actually symmetry. Okay, these two. So of course I don't look at this one because this is a 0 at number 5. At number 5 is supposed to be 2 pi. So that 2 pi is supposed to be equals to 0, which is equals to 8. But we don't plot that. Okay, DFT doesn't count that because if not, it will be repeated. So this is the magnitude, supposed to be symmetry. And this is a phase, supposed to be anti-symmetry. All right. Okay. Finish. So we have finished this topic. Any questions? Yes, I hear something. Or maybe any question from, yes?
The final answer that we want would be the
final answer. In this example, of course, actually it's not clear. Well, what does it need? So it just says that compute DFT. Okay. So, but of course, in test and exam, so the question will be precise. It will ask you precisely on which one. So if it needs on magnitude, it will ask you for magnitude. If you ask for a phase, it will ask you for phase. So if it just ask you for frequency response, so you should do the frequency response. Okay, but in this example, so
and
generally
the stuff that you have skipped just now, Doctor, do we have to like read it for this,
the one that I skip, yes, it will not be emphasis this semester. So I'm not saying that it's not 100% not related to whatever we have learned, but it's not emphasis a lot on the exam. Okay, so the exam will not be focused on those topics which I skip. Right, so actually that's another hint. So what is the hint? What will be in the final exam? So well, not in the final exam. What will be not in final exam? Okay, is the one that I skip. Okay, so just watch again. Actually, not only this week, even from all the previous week, topic which I skip is actually will not be in final exam. Right? So because we have a lot of a break actually, so that's why actually I skip those which is not in final exam. Right? So remember that that hint.
Noted.
Ada soalan lain? Okay, so if there is no other questions, so that will be the end of this class. Next week, we will start our topic on filter design. Okay, so see you guys again next week on not Tuesday. Tuesday will be another break, right, on Thai Pusam.
Yes.
So we will meet again on Thursday. So you will see that I will skip more topics. I will skip more topics. Right. So just focus on that one. Then you will know that which topic will be in the final exam, which topic will be not in final exam. Okay, so Assalamualaikum warahmatullahi wabarakatuh semua, and salam sejahtera. So jumpa lagi minggu hadapan.
Assalamualaikum. Thank you so much, Doctor.